Welcome to Chapter 6, all about polygons and symmetry. And today we'll be focusing on Lesson 6.1, Reflection Symmetry. So we already talked a bit about the idea of things being congruent when they're reflected. This idea of reflection symmetry is building off that concept. So, if we look at our first definition to help us make sense of this, it's the definition of reflection symmetric figure, or a symmetry line. So what it simply says is a plane figure F is a reflection symmetric figure if and only if there is a line, we'll call it line M, such that F reflected over M still results with the same figure of F. Then in that case, line M is known as a symmetry line for the figure. So if you can reflect something and it's the exact same as the original, that figure is a reflection symmetric figure. And the line that you're reflecting over is the symmetry line. So let's look at that. Looking at example 1, it says draw all these symmetry lines for each of the following letters. So with the capital E here, we only have one line of symmetry, this horizontal line through the middle, because if we reflect E over that line, it would still look exactly the same. Drawing the line of symmetry for M, there's only one vertical through the exact middle of it. If we'd reflect this, it would be the exact same. Now for the capital X. In this case, we have 4 lines of symmetry. We have the horizontal and the vertical, and then we also have both diagonals. If we would reflect over any of those 4 lines, figure is the same. And then with the capital H, we'd have 2 lines of symmetry, the horizontal and the vertical. So each of these are reflection symmetric figures. Our next theorem is known as the flip-flop theorem, which simply says if F and G are points, and F is reflected over line L, resulting in G, then G reflected over line L would result in F. So it works for points, it also works for figures. If F and G are figures, then figure F reflected over L is equal to G, and G reflected over L is equal to F. You can flip-flop the order. So G reflected over L gives us F, F reflected over L gives us G, similar to our symmetric properties of algebra. Then we have the segment symmetry theorem, which states every segment will have 2 lines of symmetry. So if we're looking at segment AB, one line of symmetry is the line that goes on forever that contains segment AB. So that would be this line here going on forever. The other line of symmetry is the perpendicular bisector of segment AB. So example 2 says draw any reflection lines through the angle. So we're just given angle ABC here. So what I want to do is I want to measure angle ABC. I measured angle ABC and it was approximately 115 degrees. So I know my line of reflection would be the angle bisector, whatever cuts that angle in half. So 115 divided by 2 is 57.5 degrees. So I know my line of symmetry has to cut this angle in half, so it would make 2 57.5 degree angles. Then we have what's known as the side switching theorem, which states if one side of an angle is reflected over the line containing the angle bisector, its image is the other side of the angle. So if I take this side, the AB, and we'll call this D, so ABD, and reflect it over line BD, it would give me the other side, which is angle CBD. And then the angle symmetry theorem says the line containing the bisector of an angle is the symmetry line for that angle. So an angle bisector is an angle symmetry line. Then it asks us in example 3 to draw a circle with center O and all of its symmetry lines. Obviously, I did not draw all of its symmetry lines because I would still be drawing symmetry lines. Any excuse me, any line through a circle's center point is a symmetry line for that circle. So as long as it passes through our center point, it is a symmetry line for that circle. So I could draw this line infinite amount of times going through the center point at different angles. So the circle symmetry theorem says the circle is reflection symmetric to any line through its center. And then we get into our last theorem for this lesson, which is the symmetric figures theorem. And this states, if a figure is symmetric, then any pair of corresponding parts is congruent. So similar to our CP-CF theorem. So if a figure is symmetric, any pair of corresponding parts is congruent. And our corresponding parts would be the parts that match up over our symmetry line or line of reflection. So in this case, if I took figure STUVWXYZ and reflected it over the symmetry line SW, that would give me S, Z, Y, X, W, V, U, T, meaning the S still corresponds with the S. The T would correspond with the Z, U with Y, V with X, and W with itself. So in this case, angle T is congruent to angle Z. Those two correspond. Angle X down here is congruent to angle V. Side or segment S to Y. So if I was connecting S to Y here, that'd be the same as connecting S to U here. TU, so if I connect TU right here, that's the same as ZY right here. And then WZ, if I'd connect W over to Z here, that would be congruent to connecting W to T. So segment WZ is congruent to segment WT. So today's lesson is just really getting you used to a couple of these basic symmetry theorems and the idea of reflection symmetric figures and symmetry lines. Obviously, as we go deeper into this chapter, we're going to expand and build upon these ideas of symmetry and corresponding parts.